All right, so skill 7 is a big one for our course. It's one that we're going to be doing every single cycle. I think the last question of all of my calculus tests are a curve sketch question. So it's going to be important to learn these steps. I'm going to go through the full calculus steps of curve sketching. It's going to seem a bit ridiculous for curve sketching of a polynomial to do absolutely all of these steps because you'll get part way through them and you'll know exactly what it's supposed to look like because you've done so much work with polynomials and advanced functions. I just want to go through the full details to get like the fully accurate sketch because that's what we'll need when we're working with weird functions later on. So to get going, what I want you to do is draw any smooth curve, so just a nice smooth curve that connects A to B. So you can go ahead and do that. And then you may remember I do have some magical skills that I showcased in the talent show. So this is a mind reading activity. I believe if I can read your mind that you drew something that looks like this. And if you didn't, then I believe that you drew something that looks like this. Those are kind of the two options for a smooth curve. I'm going to draw this one better. That connects A to B. You're either sort of, if you think about the straight line connecting A to B, you're either drawing the bowstring down, pulling the bowstring down, or pulling the bowstring up. Those are kind of the two kind of shapes you get when you connect those 2 points, if you're just connecting them with one smooth curved shape. So what I want to do now is look at the slopes on these shapes. So if I draw some tangent lines, what I want you to see is that these tangent lines are getting steeper and steeper and steeper. And these tangent lines start out steep and go less steep as we go along. So the idea here is both of these curves, the way that I've drawn the points A and B, they're both increasing curves. They're going up to the right. So in both of these curves, we know that the derivative is positive. But what's happening here is maybe this is a slope of 1, and then a slope of 5, and then a slope of 10. And then the other one's kind of doing the opposite, a slope of 10, a slope of 5, a slope of 1 maybe. So here, the slopes are increasing, and on this shape, the slopes are decreasing. Now this introduces kind of this new idea that we haven't really talked about yet, but we can think about not only how the function changes, we can think about how the derivative changes. We can get the rate of change of the derivative, which would mean that we would need to take the derivative of the derivative. And what that turns into is what's called the second derivative. And for these, the second derivative is telling me that these slopes are getting bigger. The second derivative is positive. So this is called the second derivative. And it is just the derivative of the derivative, how the slope changes. Yeah. We still there? Okay. And what's happening here is the slopes are getting smaller. The slopes are decreasing. They're going from 10 to 5 to 1, which would mean that the second derivative is negative. And then what I want to do is the same thing with decreasing shapes. Again, I'm going to set up an A and a B so that the curve definitely decreases. So in both of these, the derivative is going to be negative. and see if you can draw the two different shapes. So one might look like this, and one might look like that. And now let's figure out what's going on with the second derivative on these shapes. So again, I'll draw some tangents on to help us out. And what's happening here, now these slopes are all negative. These slopes are getting steeper, which in the negative sense means they're getting more negative. They're going from like -1 to -5 to -10 if I use my made up numbers. And these start out really steep, start out really negative, -10, -5, -1, and they get less and less steep as they go. Which means, this is a bit confusing, the numbers are getting larger, but since they're getting more negative, it means that the slopes are getting smaller. The slopes are decreasing. They're getting more negative. So the second derivative here is negative, and the second derivative here is positive, because they're getting less negative here, -10, -5, -1. They are increasing. And so when we do a curve sketch with calculus, we're going to, if we're getting the full details, we're going to decide not only where certain points should go, we're going to have to find max and min points like we've been, and we're going to have those on our graphs, all the local max and mins, all the turning points. We're also going to decide which of these four shapes each part of the curve should be. So we're going to get the first derivative, and that will tell us whether it's increasing. So these two curves were increasing and increasing, and this curve was decreasing and decreasing. And then the second derivative, well, here's where the second derivative are both negative at those shapes, and these outside shapes are where it's positive. And if you look at these shapes, what we're kind of getting is that shape. We're getting a frown. In, if this was a parabola, we would say that that parabola opens down. If I put these two shapes together where the second derivative is positive, if I draw that one and then that one, I get a smile. If we were thinking about just parabolas, we'd say opens up versus opening down. So when the second derivative is negative, our curve should be kind of opening down, and the proper math term for that is concave down. They are concave down if they're opening down. And if the second derivative is positive, concave up and concave up. So putting those two pieces of information together, we're going to be able to get the perfect shape of our curves. And then if we get all the key points in between, we're going to have a really good sketch of what the curve should look like, almost as good as Desmos. So leave that up there if you want to pause and look at that, and then I'll keep going. Okay, so I've drawn the graph of a cubic. And what sort of we need to do is we need to figure out in calculus terms, if I'm going to draw this cubic really nicely, what am I going to want to find? So I would think for sure we would want, if we can find them, to graph those 3 points accurately. So we will want the x and y intercepts. And that's something that you've done lots and lots in advanced functions, and that's something that we're going to want on our graph perfectly well. We're going to want these points as well, and these points you couldn't find in advanced functions. I mean, Marshallin had you plug in a value halfway between to guess, but that's not exactly where it's going to be. It was a guess at where that's going to be, but now we can find those points exactly because we know, oh, that's where the derivative is going to be 0. That's going to be our turning points. We can find them exactly. So we can find our turning points. Or local max and mins, however you want to say it. And those are going to come, what we'll see is by splitting it into intervals. We're going to have the functions increasing, first derivative is positive. At this point, first derivative is 0. First derivative is positive, first derivative is negative. At that point, first derivative is 0, and then first derivative is positive again. That's a minus sign with a VE, or a plus sign with a VE is how I write. So these intervals are going to be important. And those intervals are also, when we do those, we're going to find the turning points at the exact same time. Now, if I go back and think about these different shapes and thinking about drawing the shapes, well, this is increasing and concave down, and then it switches to decreasing concave down, and then it's decreasing but concave up all of a sudden. It's kind of switched from opening down, concave down, to opening up. So we're going to want to actually, to get the perfect shape of our graph, we're going to have to find that point where it switches from one to the other. And my eyeballs say maybe it's there, where it's switching from concave down to concave up. And that point is called a point of inflection, which we can shorten to POI, which is a bit confusing because in grade 10 and grade 11 and probably in advanced functions, when you said POI, you meant point of intersection. So it's the same acronym because it's got the same initials. So that's a bit confusing, but we'll just keep in mind if we're talking about a single function, POI means point of inflection on that single function. If there's two functions involved, maybe we'd have to write that out specifically, because if there is two functions involved, POI might mean where those two functions cross. And that's where the graph switches from concave down. Yeah, I can spell. Concave down to concave up. And if it switches from up to down, it's also called a point of inflection. When it switches concavity, those points are called points of inflection. So we're going to find, again, that split the intervals of concave up versus down, which is going to tell us our point of inflection. And this information here, x and y intercepts, well, you could do those in advanced functions before you knew what a derivative was. That comes from the original. This information, increasing and decreasing, that comes from the actual slope of the graph. That comes from the first derivative. And this new idea of whether it's concave up or down and points of inflections come from this new idea, the second derivative, which you just write 2 primes. That's the derivative of the derivative. And by the way, if you're feeling fancy in German and you want to use Leibniz notation, that's the notation for first derivative. Leibniz notation for second derivative, d squared y over dx squared. So the squared goes on the d on top and after the whole dx on the bottom. So it looks a bit weird. But that's what the notation is for second derivative. By the way, this is like a slope, right? Slope formula. The reason why this is dy and dx, it comes from, if you think back to like science, when you did change in y over change in x, you used delta y and delta x for rate of change. Those deltas then kind of become little d's when you do derivatives in Leibniz notation. So that's kind of where that notation advanced from or came from. I don't think I ever explained that before, but that's where that came from. So, yeah. And then you're going to say, like, in advanced functions, we spent so much time looking at what the end behavior of the function. and figuring that out. Here, we're going to get end behavior for free. We don't have to think about it separately. We're going to know if we start increasing, we're going to start down here. If we end increasing, we're going to end up here. If we start decreasing, we're going to have to start up here. So the end behavior comes kind of for free from increase or decrease. In advanced functions, you had to do intervals of where the function's positive and intervals of where it's negative. And again, we're going to get that for free, right? Because we're going to have the x-intercepts, and we're going to know, well, it's increasing through that intercept. It's going to go from negative to positive through that intercept. It's decreasing through this. It's going to go from positive to negative. So we don't have to find that separately anymore. What else do we get for free? Let me try and think of what else you do in advanced functions, course that I've never taken or taught. Let's see. What was the other thing? Oh, like you thought about like bounce roots, where like the x-intercept was this, and then it does that instead of going straight through. Again, we get that kind of idea for free because we're going to see that that's a turning point separately from the derivative. So we don't have to think about, well, when we factor it, that's a bounce root, or again, like what you called like a cubic root where it does this and that. Again, we're going to see that that's actually called a point of inflection, right? Because it switches from down to up there. So again, those sort of ideas all come from for free if we can do these three things. Okay, so what I'm going to do now is we're actually going to go through all these steps. So I'm going to find my x-intercepts first, which means the y value is 0. So I'm going to set this function to 0, and I'm going to have to factor it. Luckily, there's an x in common, so I can factor it pretty easily. If it wasn't an x in common, if there was like a +4 there, well, you'd have to go through your kind of guess and check to find the first root and then do synthetic division from there. So that is something that you should have in your tool bag from advanced functions. And that's going to be multiplies to -9 and adds to 3. Does that factor? Doesn't seem like that factors. So, quadratic formula, I guess. Yep. And we see -3 plus or minus square root of 9 minus 36, so something negative. So we get no other roots. So we have just x equals 0 as our only x-intercept. And my picture indicates that there should be other roots if I drew the right thing. Maybe I didn't. Let's plow ahead and see what happens. Or maybe I'll pause and make sure I'm not doing something silly. Okay, I'm back from my pause, and yes, I am doing something quite silly, so stop screaming at your screen. That's a -9, so I'm going to get some roots here. So that's going to be 9 plus 36 in there, all over 2. Root 45, so there doesn't factor because that's not a nice square root. And if we break that into 2 and go to our calculator, the numbers we get should be something like -4.85 and positive 1 point, what is it, 854. Okay, so we'll leave that as that. So those are our 3 x-intercepts. No, we'll just say 4.9 because we're graphing anyway, and 1.9. So there we go. So we've got 3 x-intercepts. Ta-da! And for y-intercept, well, we've already found it. It's goes through the origin. If I plug in 0, I get 0. So there we go. So we've got our 3 key points there for x and y intercepts. Now we're going to do some calculus. So we want to get the intervals of increase and decrease next, which is going to be coming from the derivative. So 3x squared plus 6x minus 9. That looks good. If we're going to want to find the intervals of increase and decrease, we're going to want to factor this. I see a 3 is going to factor out. That should make our life easier. And this one looks like it does factor x plus 3, x minus 1. Wonderful. So from there, what I'm going to do, if I want to get intervals of increase decrease, I need to see when this thing is positive and when it is negative. So we know when it's 0 at x equals negative 3 and x equals 1. That's when it's 0. Those are likely our turning points, but technically we don't know that quite yet. We do know for sure that the graph flattens out there because it's got a horizontal tangent there, but it might not be a turning point. It might look something like that. Now, knowing this is a cubic and we've got 2 of them, yeah, we're going to get maxes and mins there, but let's pretend we don't know what we're looking at quite yet. So how I do my factor table, and I'm not sure if Marshall showed you my way of doing it, but I do them sort of flipped from his standard. I think it works a lot better. So along the top, I kind of make a number line. I start at negative infinity, and along the top, I put all the numbers that make this thing 0. Get a 0 anywhere, because that's where it might change signs. So negative 3, positive 1, and then off to infinity. So I kind of think of that as my number line. And that works because these are x values, so this kind of looks like what our x-axis is going to look like in a second. So my intervals are from negative infinity to negative 3 to positive 1, 1 to infinity. And then along the side, sort of to the left of negative infinity, as it is a table, still, I'm going to put my 3 factors. So my 3 factors are the number 3, x plus 3, x minus 1. Those are my 3 factors. And then from there, I ask myself, the number 3 is a positive number. Doesn't matter where x is. X plus 3 changes signs at negative 3. If you're less than negative 3, you're going to be negative. If you're more than negative 3, that'll be positive, because it's 0 at negative 3. This one changes sign at 1. If we're less than 1 and you subtract 1, you get a negative answer. If you're more than 1 and you subtract 1, you get a positive answer. And then I can put all those pieces together and say, overall, my derivative is positive, and then negative, and then positive. Which means that my function is increasing, decreasing, and then increasing on those intervals. And every time I have one of these tables, I talk about what's happening at these border points here. So at negative 3 is there because it makes the derivative 0. So we have a horizontal tangent there. I'll make note that I have to flatten out there just to remind myself. Now, how we figure out what's going on is that the function increases, flattens, and then decreases. That's got to be a local max. And then this one, again, it's a horizontal tangent. It makes the derivative 0. Let's remind ourselves of that. This one's the opposite. It decreases, and then it increases. So that's got to be a local min if it flattens out in the middle. And then if our table looked something like positive and positive on either side, and it was still a horizontal tangent there, that's what it would look like if it's got that kind of cubic shape, and it keeps going, so it flattens. And then it keeps going. So that's why I put this note here to remind myself, well, I do have to flatten at that point, even if it's not a turning point. So from there, these are now key points on our graph. So what we're going to have to do is we're going to have to get the actual point. And to get that actual point, we have to plug into the original function, which is going to look like x cubed plus 3x squared minus 9 times x. Oh, it's going to test my 3 times tables. 3 cubed is 27. 3 squared, and that'll be negative still with the 3 negatives. Negative 3 squared is positive. Times 3 again is 27 as well. And then at the end I have 2 positive 18. No, positive 27. Come on, Mr. Clement. I just did that multiplication. Okay. Looks like that comes out to be 27. So that should be our local max point at 3 and 27. And now let's do the local min point, plugging in 1. I'm just double checking to make sure I did that right, because I've already screwed up once. So let's just... I bet I can do the 1. Okay, so that's 1 plus 3 is 4, take away 9 is negative 5. So those are our exact values that we're going to put on the graph as well. And yeah, there we go. So now I know it's a cubic. I know we've got now our exact max and mins. We've got our x-intercept. So I know like we could perfectly draw this at this point, but I'm just going to show you this second derivative step as well. So when I find the second derivative, this is going to get us our shapes, our concavity. When I find the second derivative, this version of the derivative was very nice to figure out when it's positive and negative to get my increasing and decreasing. But this version of the derivative is very nice to get the second derivative from. So I'm going to go back to there. And again, the second derivative is just the derivative of that. So it's going to be 6x plus 6. So just the derivative of that first derivative. And that's how the slope changes. And that's going to tell us our concavity. And we're going to want to know where this thing's increase, or where this thing's positive and negative to show where it's concave up and concave down. So I would factor out that 6, and we'll see that that thing's 0 at negative 1. And again, ridiculous to be doing this. But I'll make my factor table of this straight line. We have a 6, and we have an x plus 1. 6 is always positive. You might say, do I need to put that 6 there or that 3 there that I factored out? Do I need to include that as a factor in my table? I always do, because keep in mind, if you had factored out a negative 3, these would all be negative, and it would switch everything at the bottom. So if you don't have it there, you're going to get all the wrong answers. So make sure you put your constants in, just so you don't make silly mistakes. X plus 1, if you're adding 1 to x, you'll get a negative if you're less than negative 1, and you'll get positive as long as you're more than negative 1. So overall, our second derivative is negative, and then it's positive. And again, the idea here is that tells us that this curve starts concave down, and it switches to concave up. So it's changing the shape of the graph there. And negative 1 has that fancy name. It is a point of inflection. And it's not a horizontal tangent, because the derivative wasn't 0 there. So we're going to switch shapes, but we're not flattening out here. And again, that's a point that I'm going to want on my graph. So I'm going to plug negative 1 into the function. What is it? Plus 3x squared minus 9x. And I'm going to get negative 1 minus, no, plus 3, and then plus 9. So that looks like 12. Take away 1, 11. So I should get negative 1 and 11 as my point of inflection. And then definitely, we can for sure draw it now perfectly. But I'm going to go yet one step further and do what's called a combined table. And what the combined table is I'm going to take my two factor tables and I'm going to combine them. So I have at the top of here, -3 and 1, and I also have a -1 in the second derivative. I'm going to put all my intervals, so I have a -3, a -1, and a +1. That's when anything can change about this curve. And here, I'll put the first derivative. The first derivative was positive up until -3. It was negative between -3 and 1. So I'm going to translate that into here. Negative up until 1, I believe. Yeah, that's where the 1 is. And then positive after 1. So translating that, it's the same factor table. I'm just breaking in the middle of this negative interval. My second derivative now is concave down to start, concave up afterwards. And what you don't do here is you don't go minus, plus, minus, plus. That tells you nothing, because at no point are we multiplying the derivative and the second derivative. We're never multiplying that. So what I'm doing there, I'm not seeing what sign would result in that. What I'm doing here is I'm seeing what shape results from these two things being put together. And again, this isn't something that I have memorized, but it is those 4 shapes that we talked about at the start. So here, first derivative, increasing, positive. Second derivative, negative, concave down. I need to draw something that is increasing, concave down, increasing, and frowning. There's another way to think of that. Increasing part of a frown. So think about your 2 dots being set up to be increasing, and draw this frowny shape. And then decreasing, but staying on the frown. So set up your dots to be decreasing, still be concave down. Decreasing still, but now we're going to switch to a concave up, a smiling shape. And then our last interval, increasing, concave up, and increasing part of the smile. So again, not something I have memorized. I go through that little logic, increasing smile, decreasing smile, okay, to get my right shape. And now I can say I am ready to draw my fully detailed sketch. And it's going to be wonderful. So I'm going to scroll way back up and look through my notes. We've got -4.9, 1.9, and 0 as our x-intercepts. So maybe 1, 2, 3, 4, 5, -4.9, 0, and 1.9, 3, 4, 5, something like that. Those are our x-intercepts. Let me just make sure I got the signs of those right. Yep. Okay. Now, our next key points are at -3 and 27. So -3, somewhere way up here, we'll put 27. And then 1 was -5. So thinking about the scaling, if that's 27, -5 might look maybe a fifth of that. That looks right. Like that. And then our last key point is that point of inflection, -1 and 11. Positive 11, I believe. Yeah, better be. -1 and 11. Thinking about the scaling, maybe around there compared to 27. So from there, those are my points. And what I'm going to do is I'm going to play connect the dots. I'm going to remind myself in this first derivative table, I have horizontal tangents. At this point, I'll draw my tangent there, and at this point, I'll draw my tangent there. And so what I have to do up until -3, we have to have this shape, and I need to flatten here. So I don't have to think about end behavior. I know if I'm going to start with that shape, it's going to look something like that. It's going to hit that x-intercept, and it's going to keep that shape all the way up to that local max. And I'm going to be careful to flatten out there. And then we're going to switch to this shape and keep that shape all the way to -1, so to here. And we don't flatten that -1, we just draw that shape. And then from -1 to 1, so up until the local min, we're going to have switch to the concave up shape. Bada boom. And then after that, again, we're flattening at the bottom. After that, keep that shape. And that's how we're going to get a beautiful sketch of that graph. And you can plug it into Desmos and see that you've got the exact same thing as Desmos, which is nice to see. So that's our lesson. Those are our full steps for curve sketch. I would kind of encourage you to kind of make notes on what you're looking for in each of the 4 parts. So x and y intercepts, get the first derivative, factor it, get your horizontal tangent points, make a factor table for the first derivative. That tells you the increasing, decreasing. Then look at the borders and see, do you have a local min, a local max, or just a squiggle? Second derivative tells you the smiling versus frowning. Again, get the second derivative, factor it, do a factor table. When it's negative, it's concave down. When it's positive, you're drawing concave up. Anytime it switches, that's called a key point. That's called a point of inflection. Get your y values. And then kind of mush your 2 tables together, get all your special x values at the top, and then think about what did those 2 signs together give you for a shape. And then get your dots, connect the dots.